Welcome to Quantum Operators Masterclass. We will be taking a conceptual deep dive into the mathematical verbs that form the grammar of reality. We begin with Part 1, the core concept. We are shifting our focus from static variables to dynamic actions in the quantum world. In classical physics, properties like position and momentum are static numerical nouns. In contrast, quantum mechanics defines properties as dynamic verbs, where an operator is an instruction for a mathematical action on a state. We use the caret or hat notation represented by a to denote an operator. It signifies a transformation, not a value, acting on a wave function to extract information. Operators have three key characteristics. They take a function and output a new function. They must be linear to maintain superposition, and every measurable physical quantity or observable has a corresponding operator. Moving to Part 2, measurement. This section addresses how we extract numerical results from abstract quantum waves. When we apply an operator, we are posing a question to the particle. If the particle is in a special state, called an eigenstate, the operator returns the same state scaled by a number, known as the eigenvalue. As Paul Dirac stated, the mathematical formalism of quantum mechanics is a set of rules for calculating the probabilities of different outcomes of experiments. The eigenequation's anatomy consists of the operator A, which is the question, the eigenstate psi, which is a stable state, and the eigenvalue A, which is the numerical result. Here is a table mapping common observables. Notice how simple classical variables transform into complex quantum operators, such as position remaining a multiplication and momentum becoming a derivative. Part 3 focuses on the position operator, often called the operator of where. The position operator is simply multiplication by the coordinate x. Its physical meaning is that it weights the probability amplitude by its location without changing the shape of the wave. The formula for the position action shows that the operator acting on the wave function is just the coordinate times the wave function. A position eigenstate would be a theoretical, infinitely sharp spike, but most particles are spread out. This operator is used to find the average position of the particle. Next, we examine Part 4, momentum, the operator of flow. Momentum is linked to how the wave function changes in space, which is its derivative. The imaginary unit I is included to guarantee that the results we measure are real numbers. The momentum formula shows it is proportional to the gradient or slope of the wave function, incorporating the derivative and Planck's constant. A short wavelength means high momentum. The momentum operator measures the push of the wave. The imaginary component keeps the physics mathematically Hermitian, ensuring real outcomes. We move to Part 5, the Hamiltonian, known as the boss of all operators. The Hamiltonian, or H, represents total energy, kinetic plus potential. It dictates how the system evolves over time and is central to the Schrödinger equation. The Hamiltonian combines the actions of kinetic and potential energy operators. The Hamiltonian's power lies in predicting future states, defining allowed energy levels for atoms, and describing the physical landscape through the potential energy component. Part 6 covers commutation, which shows when the order of operations truly matters. The commutator is a fundamental limit, demonstrating why we cannot simultaneously know every property of a quantum system. If two operators do not commute, the sequence of measurement changes the result. This non-commuting property is the mathematical basis for the Heisenberg uncertainty principle. The uncertainty principle states that a highly localized wave with a tight position spread must have a broad momentum spread, and vice versa. Part 7 explores the Hermitian nature of operators, which is what keeps our physics grounded in reality. Hermitian operators are critical because they guarantee that the eigenvalues, our measured results, are always real numbers. They also ensure the completeness of our quantum states. The expectation value is the calculated average result if we measure many identical particles. The formula involves, quote, sandwiching the operator between the wave function and its conjugate. Quantum mechanics provides the probabilities of different observable outcomes, rather than definite values. The evolution of operators began with Heisenberg's matrix mechanics in 1925, followed by Schrödinger's wave mechanics in 1926, which were ultimately unified by Dirac's transformation theory in 1930. To summarize, operators are mathematical tools for extracting physical information. Key operators include position, momentum, and the Hamiltonian, which represents total energy. Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics, but with operators we can at least compute its truths." In conclusion, you have mastered the fundamental vocabulary of the quantum world. Thank you for your attention. We invite you to join the conversation on the physics of action.